Deep inside a magnet in Illinois, a tiny particle is spinning the wrong way. It is called a muon, a heavier cousin of the electron. When scientists watch it wobbles a hair too much. That extra wobble should be impossible. Something we cannot see is reaching out and tugging on it. That tug is a crack in the rulebook that builds every particle in your body, every rock on this planet, every star you have ever seen. Follow that crack, and the whole universe starts to shake. A boson that weighs too much, a ghost particle with no right to exist, an invisible mass 5 times heavier than everything that glows, a push that is ripping space apart. If mysteries like this pull you in, subscribe and come hunting with us. The rules of reality are about to break. Let's begin. Picture a tiny spinning top smaller than an atom, whirling inside a giant magnet in Illinois. That top is called a muon. It is a heavier, faster living cousin of the electron, the particle that flows through every wire in your phone. A muon looks almost the same, only about 200 times heavier. And like the electron, it acts like a tiny magnet. When you drop it into a strong magnetic field, it does something strange. It wobbles. Scientists can measure that wobble with jaw-dropping care. They built a ring wider than a basketball court, cooled it, filled it with muons, and watched them spin billions of times. The wobble follows a number. For almost 80 years, physicists have chased that number, because it hides a secret about how the universe is built. Here is the strange part. The muon wobbles a hair too much. The math says it should wobble at one exact rate. The muons in the ring wobble slightly faster. The gap is tiny, smaller than you could ever see with your eyes. Yet the machines can feel it, again and again, every single time they run the experiment. This is real. Different teams, different years, the same stubborn extra wobble. So what is pushing it? A spinning magnet only speeds up if something reaches out and touches it. But the ring is nearly empty. Something invisible is tugging on the muon, something it can feel that our instruments cannot see directly. For years, that gap set the physics world on fire. If the muon feels an unknown force, or bumps into unknown particles, then our list of nature's building blocks is missing pieces. The wobble would be the first fingerprint of a hidden layer of reality. Whole careers turned toward that ring. Newspapers called it a possible new door in physics. Think of it like a detective story. The muon is a witness. It cannot tell you the name of the thing that touched it. But its wobble carries the pressure of that touch, like a bruise that proves a punch landed. Read the bruise carefully enough, and you can start to guess who threw the punch. The measurement itself is one of the most precise things humans have ever done. Imagine measuring the distance from New York to Los Angeles, about 2,800 miles, and being sure of it down to the width of a single human hair. That is the level of care poured into watching this one particle spin, and that care is exactly why the extra wobble matters so much. A sloppy measurement can be waved away. This one cannot. The muon really is doing something the simplest math does not expect. So the world was left with a crack. A tiny, glowing crack in the rules that describe every particle in your body, every atom in this room, every star burning in the sky. Follow that crack and you fall into a universe of hidden particles, secret forces and mysteries that could rewrite the textbook. But before we chase the crack, you need to see the wall it runs through. You need to understand the rulebook itself, the most powerful and most tested idea in the history of science. Because to feel why one wobble terrifies physicists, you have to know just how perfect their rulebook was supposed to be. Every particle you have ever touched obeys one book of rules. Physicists call it the Standard Model. It is the closest thing science has to a theory of everything you can hold in your hands. On a single page, it lists the basic pieces of reality and the forces that push them around. Everything you know, your bones, your breath, the light from your screen, is built from the handful of pieces on that page. The list is short. There are particles that make up matter, like the quarks inside every proton and the electrons around every atom. There are particles that carry force, like the photon, the tiny bullet of light that lets you see. Add a few more, including the famous Higgs, and you have almost the whole cast. Fewer than 20 basic pieces build the entire visible universe. The forces are short too. There is electricity and magnetism, which hold your atoms together. There is the strong force which glues the insides of every proton. There is the weak force which lets the sun burn. 3 forces, a short list of particles, and from that, everything. Now here is why physicists trust this book so deeply. It works. It works better than almost anything humans have ever written down. The Standard Model describes the world. Then it predicts it. Scientists have used the math to guess the mass of particles nobody had ever seen, then built machines and found them exactly where the numbers said they would be. When they discovered the Higgs particle in 2012, they were confirming a promise the rulebook had made almost 50 years earlier. The book called its shot, and reality obeyed. In some tests, the Standard Model matches experiments to more than 10 decimal places. To picture that, imagine predicting the exact number of seconds in 100,000 years and being off by less than a single second. No theory in history has ever been checked this hard and passed this well. So this rulebook is a fortress. It has stood against every attack for half a century. And yet the people who know it best will tell you a quiet, unsettling truth. The book is unfinished. For all its power, the Standard Model stays silent about some of the biggest questions we can ask. It says nothing about gravity, the force that holds you to the floor and swings the planets around the sun. Gravity simply refuses to fit inside the pages. It says nothing about the dark matter that seems to outweigh every star. It cannot explain why the universe is full of stuff at all instead of empty. It has no room for the strange energy pulling galaxies apart. The rulebook describes the world you can see, and then it stops right at the edge of the darkness. So physicists live with a strange feeling. They hold the most successful theory ever built, and they know for certain that it is incomplete. Somewhere out there, hidden pieces are waiting. That is why a single wobbling muon can shake an entire field. A fortress this strong should have no cracks. If even one appears, it may be a doorway, a place where the missing pieces are leaking through. So the hunt becomes simple to describe and brutally hard to do. Find a crack. Prove it is real. Follow it into the dark. But to find a crack in an invisible wall, you first need a trick for feeling things you cannot see. To catch an invisible particle, you need help from the strangest fact in all of physics. The emptiness around you is quietly boiling. Look at the space in front of your face. It seems like pure nothing. Clear it of all air, all light, all dust, and your gut says you would be left with a perfect void. The rules of the quantum world tell a wilder story. That space is churning with activity. At the tiniest scales, particles are constantly flickering into being and vanishing again, faster than any clock could catch. They appear in pairs, born from nothing, and wink out almost instantly. Physicists call them virtual particles. The empty vacuum is really a churning sea of them, popping and dying trillions of times over, everywhere, all at once. This sounds like a wild story. It is one of the most tested ideas in science. Scientists can measure the faint push these flickering particles create between 2 metal plates placed a hair apart. The plates feel a real force from a sea of particles that seems to come from nowhere. Empty space pushes on solid metal. That has been seen in the lab over and over. Now bring back our muon spinning in its ring. As the muon travels, it is never truly alone. It swims through that boiling sea. Ghostly particles flicker in and out around it, brushing against it, giving it the tiniest nudges. Each little nudge changes how the muon wobbles, by an amount so small it seems impossible to matter, but it does matter, and this is the secret weapon. The muon feels every kind of particle in that sea, including kinds we have already found. Physicists can add up all the known flickers and predict the wobble almost perfectly. Almost. Because if there are unknown particles hiding in the vacuum, undiscovered pieces of reality, the muon feels those too. It cannot help it. Anything that exists, even for a flicker, leaves its faint mark on the spin. Picture a swimmer floating in a dark harbour at night. She cannot see the boats around her, but when a boat passes, its wake reaches her, and she rocks. From the exact pattern of the rocking, she could figure out how big the boat was, how fast it moved even if she never saw it. The Sankyun is that swimmer. Its wobble is the rocking, and the wake comes from every particle in the sea, seen and unseen. That is why one tiny wobble carries so much weight. The muon is a detector with no wires and no screen. It reports on the entire hidden contents of empty space just by spinning. If its wobble is off, the most exciting explanation is that a new kind of particle is out there in the dark, flickering, brushing past, leaving a bruise on the spin. For years, that was the dream. The extra wobble looked like the fingerprint of something new. Physicists imagined heavy hidden particles, whole new forces, waiting just past the edge of the known. There was only one way to be sure. You had to add up every known flicker with perfect care, predict the exact wobble, and compare it to the ring. If the numbers disagreed, the gap was a discovery. So teams of scientists set out to calculate that number down to its final digit. And that is where the beautiful, simple story turned into a fight, one that split the physics world in two. The whole mystery came down to one number that had to be worked out by hand, and it nearly broke everyone who tried. To know if the muon wobbles too much, you need two things. You need the measurement from the ring, which scientists trust deeply, and you need a prediction, the exact wobble the standard model expects, worked out on paper and computers. The size of the crack is just the gap between them. Simple to say, brutal to do. Most of the prediction is smooth sailing. Physicists can calculate the effect of light and electricity flickering around the muon with breathtaking accuracy. Then they hit a wall. For a tiny slice of time, the muon can spit out a little storm of the particles ruled by the strong force, the quarks and their glue. That storm is a nightmare to calculate. The strong force is wild and messy, and the usual math tricks fall apart. So scientists tried two different roads to get past the storm. The first road uses real data. Instead of calculating the messy part, physicists borrow measurements from other experiments where similar storms of particles are made on purpose and counted. They feed that real-world data into the prediction. For years, this road gave a clear answer, and that answer sat below the ring's wobble. The gap was there. The crack looked real. Excitement built. The second road uses raw computing power. A different group of scientists tried to simulate the strong force directly, chopping space and time into a grid of tiny points and letting supercomputers grind through the math, point by point, for months. This method is called working on a lattice, like solving the universe one square of graph paper at a time. Then, a few years ago, the lattice teams delivered their answer, and it clashed with the first road. The supercomputer prediction came out higher, closer to the ring's wobble. If the lattice was right, the gap shrank, and the exciting crack faded toward nothing. The muon might be behaving exactly as the rulebook says after all. Suddenly the field had a new problem. Two careful predictions of the same number disagreed with each other. One hinted at hidden new physics, the other hinted at no crack at all. Both used real science. Both were checked and rechecked by serious people. By 2025, the teams working on the official prediction leaned toward the supercomputer answer, and the famous gap looked much smaller than before. For many physicists, the dream of a clear crack in the muon's wobble had dimmed. This is how real science actually works. The crack was honest science, and the excitement made sense. Scientists simply found that the ground under the prediction was shakier than they thought. Now they are digging into why the two roads disagree, because that disagreement is itself a mystery worth solving. The muon story is a warning and a lesson at once. A crack is only real if both the measurement and the prediction are rock solid. Shake either one, and the crack can vanish like a shadow at noon. So physicists did something clever. They turned to a particle they understand far better than the muon, one whose wobble they can predict with almost perfect confidence. They turned to the electron. And there, in the most precise measurement humans have ever made, they found a different kind of trouble. The electron gives us the single most accurate prediction in all of science. And hiding inside that triumph is a quiet crack. The electron wobbles in a magnetic field just like its heavier cousin the muon. But the electron is far simpler and far calmer. It barely bothers with the messy strong force at all. That makes its wobble something physicists can predict with almost unbelievable confidence. And when they compare their prediction to the real measured wobble, the two agree to about 12 decimal places. Try to feel how staggering that is. Imagine measuring the distance across the United States coast to coast, roughly 3,000 miles, and having your answer be correct down to the width of a single human hair. That is the level of agreement between theory and experiment for the electron. Nothing else humans have ever tested comes close. It is the crown jewel of the whole rulebook, proof that our deepest math truly matches the world. So the electron looks like the hero of the story, the particle that behaves perfectly. And it almost is. Here is the trouble. To make that perfect prediction, physicists need to feed in one crucial number first. It measures the strength of electricity and magnetism, how firmly charged particles pull and push on each other. This number is one of the most important constants in nature. Nearly every calculation about light and atoms depends on it. To test the electron, you must know this number with staggering precision, measured on its own in a completely separate experiment. And that is where the crack appears. Scientists measure this number in more than one way. In one method, they track how a single atom recoils when it soaks up a particle of light, and from that recoil they read off the number. Two of the best teams in the world ran versions of this experiment, using different atoms and different setups. Both are brilliant, both are careful, and they came back with answers that disagree. The gap between them is small, far too small to matter in daily life. But for measurements this precise, the gap is a scandal. Two of the finest experiments on Earth, trying to measure the same fundamental number, do not match. One of them is wrong, or something strange is going on, and nobody yet knows which. This matters far beyond one dusty constant. If we cannot pin down the strength of electricity itself, then we cannot fully trust our test of the electron's wobble. The crown jewel comes with a scratch. The most precise agreement in science leans on a number that two great labs cannot agree on. Picture two master watchmakers, each building a clock so perfect it loses less than a second in a million years. You set the clocks side by side, sure they will tick as one. Instead, slowly, they drift apart. Both cannot be right. And until you find out why, you cannot fully trust either one. So even in physics' proudest success, a small crack hides in the foundation. It might be a subtle mistake in one experiment, waiting to be found. Or it might be the faint edge of something deeper we do not yet understand. The lesson keeps repeating. The closer we look, the more cracks appear, even in the places we thought were solid. And when physicists turned from these feather-like particles to a heavy, powerful carrier of force, the next crack came roaring. In 2022, one experiment measured a single particle and set off a shockwave that reached every physics lab on Earth. The particle is called the W boson. It is one of the carriers of the weak force, the force that lets stars shine and lets certain atoms break apart and change. The W boson is heavy, far heavier than the protons inside you, and it lives for only a flicker before it decays. You will never hold one, but its mass is one of the most important numbers in all of physics. Here is why. The rulebook ties the W boson's mass to a web of other numbers. Once you know the masses of a few other particles, the standard model tells you, with great precision, exactly how heavy the W boson must be. It is like a puzzle where the final piece has only one possible shape. Measure the W boson, and you are testing whether the whole web holds together. For years, measurements matched the prediction, and the web held. Then a team at a machine near Chicago, called the Collider Detector at Fermilab, spent a full decade poring over their data. They counted, checked, and rechecked millions of these particles. And in 2022, they announced their answer. The W boson was too heavy. The gap they found was huge. In the language physicists use to measure surprise, it was about 7 standard deviations away from the prediction. That is the kind of number that, if it holds, means discovery. It screamed that something was wrong with the web, that hidden heavy particles might be secretly changing the W boson's mass from the shadows. For a while, it looked like the biggest crack in decades. The physics world lit up. Hundreds of papers poured out, each trying to explain the heavy W boson with some new particle or force. If the Chicago result was right, the rulebook had finally truly broken. Then came the test that mattered. Other teams had to measure the same thing. At the largest machine ever built, the Large Hadron Collider near Geneva, a giant experiment took its own careful shot at the W boson's mass. They worked for years using a huge pile of data and a fresh set of methods. In 2024, they revealed their number. Their W boson matched the prediction. The Webb held after all. So now there were two measurements of the same particle, staring each other down. One said the W boson was strangely heavy and the rulebook was cracked. The other said everything was fine. They could not both be right. Most physicists now lean toward the ordinary answer, the one where the standard model wins again. The suspicion is that the shocking Chicago result may hide some subtle flaw, a tiny bias buried deep in a decade of complicated work. The teams are still digging, still arguing, still checking. This is a different kind of lesson than the muon or the electron. Sometimes the crack lives in the ruler we use to measure reality. A hidden mistake can dress itself up as a discovery. Telling the two apart is the hardest and most important job in all of science. But some cracks cannot be blamed on a broken ruler. Some come from the rulebook demanding something that looks flatly impossible. And the strangest of those cracks sits inside the most famous particle of this century, the one that gives everything its mass. The particle that hands out mass to everything else has a mass of its own that should not be possible. Meet the Higgs, the most talked about particle of our time. When scientists finally found it in 2012, it made headlines around the world. The Higgs matters because it fills all of space with an invisible field, a kind of cosmic honey. As particles move through that honey, they get slowed down, and that dragging is what we feel as mass. Without the Higgs field, the electrons in your body would race around at the speed of light and no atom could ever form. You exist because of that field. So the Higgs is the giver of mass, and that is what makes its own weight so deeply strange. Just like the muon, the Higgs feels the boiling sea of virtual particles flickering in empty space. Those flickers tug on its mass. But because the Higgs is special, the tugs do not stay small. The math says they should pile up, pulling the Higgs mass higher and higher, hauling it up toward the most extreme scale in all of physics, the scale where gravity itself turns quantum. How big is that scale? It is heavier than the Higgs we measured by a factor with more than 16 zeros after it. The natural expectation is that the Higgs should be crushingly, absurdly heavy, dragged up by the vacuum to a mass almost beyond imagining. Instead, the Higgs is light, light enough to build a gentle universe full of atoms and stars and people. For that to happen, the enormous tugs from the vacuum have to almost perfectly cancel out. Giant upward pulls and giant downward pulls, arriving from the churning sea, have to line up and erase each other down to dozens of decimal places, leaving behind only the tiny friendly mass we see. If even one digit were off, the universe would look nothing like this. Physicists find that almost impossible to swallow. They call it the naturalness problem, and it keeps them up at night. Nature seems to have balanced a mountain on the point of a needle and held it there, perfectly, since the beginning of time. Picture rolling a boulder down a rocky hillside, bouncing and crashing, and having it come to rest standing upright on a single small pebble at the bottom, balanced flawlessly, with no hand to steady it. You would not call that luck. You would be certain that something you could not see was holding it in place. That is exactly how the Higgs mass feels. Something seems to be steadying it. Some hidden rule, some unseen structure, some particles we have not met, quietly cancelling the vacuum's giant pulls. The lightness of the Higgs may be a clue pointing straight at physics beyond the rulebook. This crack is different from the muon or the W boson. It rests on two rock-solid facts. The Higgs really is light, and the boiling vacuum really should drag it heavy. The gap between those two facts is a genuine hole in our understanding, and it is enormous. So for decades, physicists chased the most beautiful idea anyone had ever dreamed up to fill that hole. A hidden symmetry so elegant it seemed almost too good to be false, one that would give every particle a secret partner and steady the Higgs for free. They were so sure they would find it that they built the greatest machine in history to go hunting. And what happened next shook their faith to the core. Physicists fell in love with an idea so beautiful they were certain nature had to use it, and then nature refused. The idea is called supersymmetry. It offers a stunning fix for the puzzle of the Higgs. Remember, the trouble was that the boiling vacuum should drag the Higgs mass up to something monstrous, yet the Higgs stays light. Supersymmetry says the tugs cancel for a simple reason. Every particle we know has a secret partner, a heavier twin, and the twins pull in the opposite direction. Every matter particle would have a force-like partner. Every force particle would have a matter-like partner. As the vacuum tugs the Higgs one way through the ordinary particles, it tugs the other way through their twins, and the two effects wipe each other out. The mountain stays balanced on the needle, held there by a deep hidden rule instead of blind luck. The Higgs stays light naturally with no impossible fine-tuning. The beauty did not stop there. The lightest of these twin particles had a bonus feature. It would be heavy, stable, and nearly impossible to see, drifting through the universe unnoticed. That description matched almost perfectly the dark matter that seems to fill every galaxy. In one elegant stroke, supersymmetry could steady the Higgs and explain the invisible mass of the cosmos, two of the deepest mysteries in physics, solved by a single idea. Physicists were smitten. For decades, supersymmetry was the favourite bet for what lay beyond the rulebook. Thousands of scientists built their careers around it. Textbooks were written. The theory was so elegant, so powerful, that many were sure it simply had to be true. There was one way to find out. Build a machine violent enough to create the twins. That machine became the Large Hadron Collider, a ring of tunnels 17 miles around, buried beneath the border of France and Switzerland. Inside it, protons are slammed together at nearly the speed of light, recreating conditions from the first slivers of a second after the universe began. If the twin particles existed anywhere in reach, the collider should have smashed them into being. Scientists watched their detectors, hungry for the first sign of a superpartner. They watched for years. The collisions piled up into the trillions. The detectors caught everything, and the twins never appeared. Search after search came back empty. The simplest, most beautiful versions of supersymmetry predicted partners light enough for the machine to make, and those partners were nowhere to be found. One by one, the elegant possibilities were crossed off. The theory that was supposed to be waiting just around the corner kept retreating into the shadows. This was a gut punch for physics. A whole generation had bet on supersymmetry, and the greatest machine ever built had come up empty. The idea still clings to life. The twins might still exist, hiding at masses too heavy for even this collider to reach. But the dream of an easy, elegant answer took a brutal blow. It left physicists with a humbling thought. Sometimes an idea can be gorgeous, powerful, and deeply satisfying, and still turn out wrong. The universe is under no obligation to match our sense of beauty. So the hunt for cracks went on, and the next one did not come from a giant collider or a fancy theory. It came from the most common, most ignored particle in the entire universe, a ghost that pours through your body by the trillion every second of your life. And that ghost was quietly breaking one of the rulebook's oldest promises. Right now, trillions of ghostly particles are passing straight through your body, and they just shattered a rule the rulebook swore could never break. They are called neutrinos, and they are the most slippery things in nature. They have no electric charge. They almost never bump into anything. They stream out of the sun in unimaginable numbers, race across space, and pass through planets as if the planets were not there. About 100 trillion of them fly through your body every second. You have never felt a single one. To stop even half of the neutrinos from the sun, you would need a wall of solid lead about 1 light-year thick. That is a slab of metal stretching almost 6 trillion miles. Neutrinos simply do not care about matter. They slip through the whole Earth without slowing down, like wind through an open window. For a long time, the rulebook made a firm promise about these ghosts. It said neutrinos have no mass at all. They should be weightless, like particles of a light, forever zipping along at the universe's top speed. That was the rule, clean, simple, and wrong. The cracks showed up when scientists tried to count the neutrinos coming from the sun. They knew how many the sun should make. They built enormous detectors deep underground, huge tanks of liquid buried in mines to block out everything but neutrinos. Then they counted, and they kept finding too few. Around 2 out of every 3 neutrinos were missing. The answer to that mystery rewrote the rulebook. Neutrinos come in 3 types, 3 different flavors, and it turns out that as a neutrino travels, it can quietly change from one flavor into another and back again, shifting its identity along the way. The detectors were only good at catching one flavor, so when the others transformed in flight, They slipped by uncounted. The neutrinos had been there all along. They were simply travelling in disguise. This shape-shifting is called oscillation, and here is the part that broke the rulebook. A particle can only change flavour in flight if it has mass. Something with zero mass moving at the speed of light can never change. The very fact that neutrinos oscillate proves beyond doubt that they weigh something. The promise of massless neutrinos was simply false. This was confirmed so solidly that it earned a Nobel Prize. It stands today as the first crack in the standard model that everyone agrees is real. The rulebook said one thing and the universe said another, and this time there is no argument about which one is right. Picture a coin flipping end over end as it flies through the air. Heads, tails, changing the whole way. Now imagine a coin with no thickness at all. Flat as a shadow, it could never flip. The fact that neutrinos flip in flight tells us they have real substance, real weight, no matter how tiny. That single fact cracked the rulebook open and let the daylight in. If the book was wrong about something this basic, what else might it be missing? The most common particle in the universe had just proven that our best theory was incomplete, and it raised a question that sounds childishly simple and turns out to be maddeningly hard. The neutrino has mass, so exactly how heavy is a ghost? The race to answer that has pushed scientists to the very edge of what a scale can do. We know the neutrino has weight, and yet weighing it has become one of the hardest challenges in all of science. The shape-shifting of neutrinos proved they carry mass. But it came with a frustrating catch. The oscillation only reveals the difference in weight between the three flavours, like knowing that one child is taller than another without knowing how tall either one is. To find the true weight of a neutrino, scientists needed a completely different attack, and the target is brutally small. A neutrino is so light that the electron, already one of the lightest particles known, is at least hundreds of thousands of times heavier. Trying to weigh a neutrino is like trying to weigh a single fingerprint on a truck. The thing you want to measure is buried under mountains of much heavier stuff, so physicists went after the ghost in a clever, indirect way. Deep in Germany, they built a machine the size of a house for one delicate job. It watches a special kind of atom fall apart. When that atom decays, it flings out an electron and a neutrino together, and the two of them share a fixed budget of energy between them. If the neutrino has weight, it must carry away at least a little energy just to exist, which means the electron can never grab quite the full budget for itself. So the scientists measure the electrons, millions upon millions of them, hunting for the exact top edge of their energy. The neutrino's mass hides in that edge, in the tiniest sliver of missing energy at the very peak. It is a measurement so fine that the machine has to sort energies with almost impossible care, chasing a whisper at the edge of a roar. So far, the answer is simple to say and stunning to think about. The neutrino is even lighter than the tightest earlier guesses. Scientists have not yet caught its exact weight. They have only squeezed the ceiling lower and lower, proving the ghost is lighter than almost anyone imagined. The true number is still unknown. There is a second, wilder way to weigh a neutrino, and it uses the entire universe as a scale. Because neutrinos flooded the early cosmos in staggering numbers, their tiny mass, added up across all of space, gently tugged on how galaxies formed. By mapping how matter is spread across the sky, scientists can read off a limit on the neutrino's weight from the shape of the universe itself. A particle almost too light to measure leaves its fingerprint on structures billions of miles wide. Both Rhodes, the house-sized machine and the map of the cosmos, agree on the strange truth. The neutrino weighs something, and that something is astonishingly close to nothing. Why so light? Nobody knows. The rulebook offers no reason for it. Some physicists suspect the neutrino gets its featherweight mass through a secret mechanism, a hidden trick involving heavy, undiscovered partner particles lurking far out of reach. If that guess is right, weighing the ghost could point us toward a whole new layer of reality. So the neutrino keeps its secret dangling just past our instruments. We know it has weight. We know that weight is tiny, and we do not know why. But the mass of the neutrino is only its first riddle. The next one is stranger, and it strikes at the very idea of what a particle is, because there is a real chance that the neutrino is its own opposite, its own antiparticle, a thing no other piece of matter can claim. Every particle has an opposite, a mirror twin made of antimatter, except possibly for one, and that exception could explain why the universe exists. Antimatter sounds like science fiction, and it is completely real. For nearly every kind of particle, there is a matching antiparticle with the opposite charge. The electron has the anti-electron, a particle with the same weight, but a positive charge instead of a negative one. When a particle meets its antiparticle, they destroy each other in a flash of pure energy. Matter and antimatter cannot share a room. They annihilate. This is a strict rule for the particles that make up you. Your electrons are clearly different from anti-electrons. Your quarks are clearly different from antiquarks. Matter and antimatter, always two separate things. The neutrino might break even that. Because the neutrino has no electric charge, it lives in a strange grey zone. A charge is the easiest way to tell a particle from its antiparticle, and the neutrino simply has none. So physicists face a haunting question. Is the antineutrino truly a different particle? Or is the neutrino secretly its own antiparticle, the only piece of matter that is its own mirror twin? If that second answer is true, it would be one of the deepest facts in nature. And there is one rare event that could prove it. Deep underground, scientists watch certain atoms that decay in an unusual way, spitting out 2 electrons and 2 neutrinos at once. That double decay is rare but well understood. Now imagine the neutrino is its own antiparticle. Then, once in a blue moon, the 2 neutrinos in that decay could quietly cancel each other on the way out, meeting and erasing each other before they ever escape. The atom would fling out 2 electrons and no neutrinos at all. That silent version has never been seen. Scientists have built detectors in the deepest, quietest places on Earth, shielding them from every stray particle, waiting for a single atom to decay with 2 electrons and nothing else. Finding even a handful of these events in years of watching would change physics forever. So far, the count stands at 0. The search continues, patient and unfinished. If they ever catch it, the payoff is enormous. It would prove the neutrino is its own antiparticle, and that alone would crack the rulebook wide. But it would do something even bigger. It could help answer the oldest question of all, the question of why there is anything here to ask it. Picture a perfectly still pond at midnight, so smooth it acts like a mirror. Drop in a single pebble. If the ripples spreading out are a flawless mirror image on every side, the water is ordinary. But if one side ripples differently, you have learned that the pond hides a secret rule, a lopsidedness you could never have guessed from the calm surface. The neutrino may hide exactly that kind of secret. And a lopsided rule buried in these ghosts might be the reason the early universe did not simply erase itself. For now, this remains an open hunt. Nobody has proven the neutrino is its own twin. But the possibility hangs there, glowing, one of the most tantalizing cracks in all of physics. And if the neutrino can surprise us this much, it raises an even wilder thought. What if the 3 neutrinos we know are only the ones we can catch? What if there is another kind, hiding so well that it ignores nearly everything, even our best detectors? A string of strange experiments keeps hinting at a 4th kind of neutrino, one so shy it might be almost impossible to ever catch. The 3 flavors of neutrino we know are already the ghosts of the particle world. They barely touch anything. Yet at least they feel the weak force, the same force that lets stars burn. That faint touch is how our detectors catch them at all. Rare as it is, once in a great while a neutrino bumps into an atom, and we see the splash. Now imagine a neutrino even more withdrawn than that. A neutrino that ignores the weak force too, that feels nothing at all except gravity, the weakest pull in nature. It would drift through the universe, leaving almost no trace, invisible even to the machines we built to catch the invisible. Physicists call this idea a sterile neutrino, because it stays apart from the ordinary forces, sterile and aloof. You might think a particle that hides that well could never be found. But there is a loophole. Neutrinos oscillate, shifting from flavor to flavor as they fly. If a sterile neutrino exists, the ordinary neutrinos could sometimes shapeshift into it, and then back again. During the time they spend as the hidden flavor, our detectors would lose sight of them, so the fingerprint of a sterile neutrino would be ordinary neutrinos, vanishing and reappearing in a pattern the 3 known flavors cannot explain. And here is the tantalizing part. Several experiments, over several decades, have seen hints of exactly that. Years ago, one experiment fired beams of neutrinos across a lab and counted them arriving in numbers that did not add up. Later, another experiment saw a strange excess of events that the three known flavors struggled to explain. Then scientists noticed that nuclear reactors, which pour out neutrinos as a byproduct, seem to produce slightly fewer than the math predicted, as if some were slipping away into a hidden flavor. Separate experiments, separate methods, all whispering the same odd word. Something extra. If those hints are real, it would mean a whole new particle, sitting just outside the rulebook, adding a fourth ghost to the family. It could reshape our picture of the early universe and maybe even connect to dark matter. But the story refuses to settle. Newer, sharper experiments were built to hunt the sterile neutrino directly, and their results have muddied the water rather than clearing it. One major experiment looked hard for the extra events, and found signs that pointed away from a simple sterile neutrino. The old hints remain unproven, and they refuse to fully die. Picture a house at night where you keep hearing footsteps in an empty room. You check, and no one is there. It happens again and again, from different rooms over many years. You cannot prove anyone is in the house, you also cannot explain the sounds. That uneasy in-between is exactly where the sterile neutrino sits today. Honest physicists will tell you plainly that nobody knows yet. So it stays a maybe, a shy possible ghost that keeps knocking and keeps vanishing before we can open the door. It might be a real fourth neutrino. It might be a string of unrelated mistakes. The hunt goes on. These slippery ghosts point us toward the greatest mystery of all, the one that towers over every crack we have seen, because the neutrino's hidden lopsidedness may hold the answer to a question so basic we rarely stop to ask it. Why does anything exist at all? Here is the most shocking fact in all of physics. By the strict rules of nature, the universe should be completely empty. Yet it is full of stars, planets, and people. Go back to the birth of the universe, to the blazing first moments after the Big Bang. In that furnace of pure energy, particles were being born constantly. But the rules of physics have a stubborn habit. When energy turns into matter, it almost always makes matter and antimatter in equal pairs. One particle, one antiparticle, born together side by side. You already know what happens when matter meets antimatter. They annihilate, vanishing in a burst of energy. So picture the early universe as a roaring sea of these pairs, constantly created and constantly destroying each other. Matter and antimatter, made in equal amounts, wiping each other out just as fast. If the rules were perfectly balanced, the story should have ended right there. Every particle of matter should have found its antimatter twin and died. The universe should have burned down to a cold, empty glow of light, with no matter left to build a single atom. No stars, no planets, no you. Yet here you are. Somehow matter won. For every billion pairs that annihilated, it seems there was about one extra particle of matter with no antimatter twin to cancel it. That leftover, 1 part in a billion, survived the great annihilation. And everything you have ever seen, every mountain, every ocean, every star in the night sky, is built from that thin scrap of surplus. We are the tiny remainder that the fire did not consume. This is confirmed beyond any doubt. Look around. The universe is made of matter. Antimatter is vanishingly rare, made only in tiny amounts in labs and in violent cosmic events. The imbalance is real, and it is total. Our whole world is the ash left over from a fire that should have burned itself out completely. The question is why? Why did the scales tip toward matter? For the universe to end up lopsided, the rules themselves must be slightly lopsided. Somewhere in the laws of nature, matter and antimatter must behave just a little differently, enough to leave that one survivor in a billion. And the rulebook, for all its power, cannot fully explain it. Picture a factory that stamps out coins, and for every coin it makes a perfect mirror image anti-coin, and the two instantly destroy each other. Run that factory forever, and you should end with an empty floor. Instead, you walk in and find the floor buried in coins piled to the ceiling. You would know at once that the machine was secretly rigged. A hidden bias, tiny but real, tilting every batch toward coins. Our universe is that impossible pile of coins. The machine was rigged. Something in the laws of physics favoured matter over antimatter, just barely, just enough. Finding that hidden bias is one of the greatest hunts in science, because it is the reason we get to exist at all. Physicists have already caught the rules cheating, just a little, in a place they did not expect. They have watched certain particles and their antiparticles behave differently, breaking the perfect mirror. It is real, and it is measured. But when they add it up, it is far too small to explain the pile of coins we live in. The known cheating cannot account for a whole universe of matter. So the search for the rest of the bias goes on, and it starts with that first, tiny broken mirror. Physicists have caught nature breaking its own mirror, cheating ever so slightly in favour of matter, and the cheat they found is real but far too small. For a long time, scientists assumed the universe played fair. They believed that if you swapped every particle for its antiparticle, the laws of physics would carry on exactly the same, like a perfect reflection in a mirror. Matter and antimatter, they thought, were flawless opposites, treated identically by the rules. Then experiments proved it false. Deep in their detectors, physicists studied certain unstable particles and their antimatter twins, watching how each fell apart. If the mirror were perfect, a particle and its antiparticle would decay in perfectly matching ways. Instead, the scientists caught a difference. The particle and its twin decayed at slightly different rates. The mirror was cracked. Matter and antimatter really do behave differently, by a small but measurable amount. This broken mirror is a confirmed fact, so important it earned a Nobel Prize. It shows that nature does have a built-in bias, a faint preference woven into the rules. For a thrilling moment, it looked like the whole answer to why we exist. Here was the rigged machine, caught in the act, tilting the universe toward matter. Then physicists did the math, and their excitement cooled. The bias they found in these particles is real, but it is tiny, far too weak to explain the vast pile of matter that fills the cosmos. If this were the only cheat in nature, the early universe would have annihilated almost completely, leaving a world billions of times emptier than the one we see. The known broken mirror can account for only a sliver of the matter around us. The rest of the bias is still missing. So the great hunt turns toward the ghosts we met before, the neutrinos. Neutrinos come in 3 flavors and shapeshift as they fly. And here is the exciting possibility. Neutrinos might shapeshift differently from antineutrinos. A neutrino might prefer to change flavors one way, while its antimatter twin prefers another. If that is true, the neutrinos could carry a much larger broken mirror than the one we've already found, maybe large enough to explain why matter won. Right now, scientists are chasing exactly this. They fire beams of neutrinos hundreds of miles through solid rock, from one lab to a giant detector far away, then do the same with antineutrinos, comparing how each shapeshifts along the journey. A beam of ghosts aimed across an entire state, hunting for the faintest hint that matter and antimatter part ways. Early results tease at a difference, a possible lopsidedness in how neutrinos and antineutrinos change. But the measurement is fiendishly hard, and the hints are not yet solid enough to trust. Bigger experiments are being built right now to settle it, machines that could finally reveal whether the ghosts hold the secret of our existence. Picture 2 dancers, one for matter, one for antimatter, told to perform the exact same routine. For centuries you assumed they moved as perfect reflections. Then you look closely and catch one dancer adding a tiny extra step the other never makes. It is small, but it means the routine was never truly symmetric, and that hidden step might be the whole reason the stage is not empty. Yet as physicists study these lopsided rules, they run into an opposite puzzle that is just as strange. Because there is one force in nature that looks too perfect, too balanced, as if someone tuned it by hand. One force in nature is so perfectly balanced that its fairness has become a mystery all its own. We just saw that the weak force plays favourites, treating matter and antimatter a little differently, breaking the mirror by a small amount. Once physicists knew that mirrors could crack, they looked at the other forces and asked a natural question. Do they cheat too? In particular, they turned to the strong force, the powerful glue that binds the insides of every proton and holds the heart of every atom together. By all rights, the strong force should be lopsided as well. The math that describes it has a built-in knob, a number that controls how much the strong force breaks the mirror between matter and antimatter. That knob could sit anywhere. It could be turned high, making the strong force wildly unfair. Nothing in the rulebook says where it must land. If that knob were turned up even a little, It would leave a clear mark on the world. It would give the neutron, one of the particles inside every atom, a slightly lopsided shape, a tiny separation of its positive and negative ends, like a little built-in compass needle. Scientists can hunt for that lopsidedness with astonishing precision. They have looked harder and harder for decades, and they have found nothing. The neutron appears to be almost perfectly balanced, with no measurable lopsidedness at all. The limit they have reached is staggering. If you blew a neutron up to the size of our entire Earth, any separation of its positive and negative ends would have to be smaller than the width of a single human hair. The strong force looks almost impossibly fair, balanced to a degree that seems suspicious. That is the puzzle. The knob could have been set anywhere, yet nature seems to have turned it almost exactly to zero, dialing the strong force to near-perfect balance. Out of countless possible settings, we got the one that looks flawlessly even. Physicists find that hard to accept as a coincidence. When a number that could be anything turns out to be astonishingly precisely zero, it usually means a reason is hiding underneath. Picture a giant sound system with 100 dials, each one able to sit anywhere from silent to blasting. Someone powers it up, and you find every dial spun to a random spot except one, which sits at exactly perfectly zero dead center without a hair of drift. You would not shrug that off. You would be sure that some hidden hand had reached in and set that one dial on purpose. The strong force is that one impossible dial, and the deep question is, what hand set it? Why is a force that could have been lopsided instead tuned to near-perfect fairness? The rulebook offers no answer. It simply leaves the knob sitting at zero and stays silent about why. This mystery is completely real and unsolved. It has a name that physicists mutter with frustration because it points at a hole in our understanding that will not go away. And the most popular idea for filling that hole is bold and beautiful. It says the knob is not frozen at all. Instead, a brand new particle quietly rolls the dial down to zero on its own, as a natural result of how the universe works. That particle has never been seen, but if it exists, it might do something even more astonishing than fixing the strong force. It might be the invisible stuff that makes up most of the matter in the universe. To explain why one force is so perfectly balanced, physicists dreamed up a featherweight ghost particle, and then realized it might also solve the greatest missing mass mystery in the cosmos. The puzzle was that strange dial on the strong force, the one nature seems to have set almost exactly to zero for no reason we can find. Decades ago, a pair of clever physicists came up with an elegant fix. What if the dial can actually move? What if a gentle force always nudges it back towards zero, the way a ball rolls to the bottom of a valley? The dial would settle at zero on its own, naturally, with no hidden hand required. But that idea came with a price, and the price was a new particle. If the dial can move, then wiggles in the dial are themselves a particle, a brand new piece of nature nobody had ever seen. Physicists named it the axion. It would be almost unimaginably light, far lighter even than the ghostly neutrino, and it would barely interact with anything at all. A whisper of a particle, born from a math trick to fix a stubborn force. For a while, the axion was just a neat idea. Then physicists noticed something that changed everything. If axions are real, the early universe should have made them in staggering numbers, and because they are so light and so shy, they would still be here today, drifting through all of space in vast invisible clouds. They would have mass, they would be nearly impossible to see, and they would gently tug on galaxies with their gravity. That description rang a very loud bell. It is almost exactly what scientists expect from dark matter, the mysterious invisible stuff that seems to outweigh every visible star 5-1. So one small particle, invented to fix the balance of the strong force, might also be the hidden mass holding galaxies together, two of the biggest mysteries in physics, possibly solved by the same ghost. Now the race is on to catch one. Since axions barely touch normal matter, scientists have to be sneaky. The leading trick uses the fact that an axion, inside a powerful magnetic field, might occasionally transform into a faint flicker of light. So researchers build sealed chambers wrapped in the strongest magnets on Earth, cool them to near the coldest temperature possible, and listen for the tiniest whisper of light that could betray an axion turning into a photon. It's like trying to hear a single snowflake landing during a thunderstorm. The signal, if it exists, would be almost impossibly faint. So far, no one has caught it. The axion remains a ghost on paper, motivated and hunted but still unconfirmed. Picture a locksmith who invents a strange new key to fix one particular broken lock. Then he walks through the city and discovers that this same odd key seems to fit a second lock on a different door, a door everyone has been trying to open for years. He has not turned either lock yet, but the fact that one key might open both is too exciting to ignore. The axion is that key. It could quiet the strong force and unmask dark matter at the same time. Whether nature actually uses it, we still do not know. While some physicists hunt ghosts to fix old forces, others chase something even bolder. Because one small experiment claims it may have glimpsed an entirely new force of nature, a fifth force, hiding inside the decay of a tiny atom. In a modest laboratory, a team of scientists fired particles at a thin target and saw something fly out that might be the sign of a fifth force of nature. You have felt four forces your whole life. Gravity holds you to the ground. Electricity and magnetism light your screen and bind your atoms. The strong force glues the hearts of those atoms together. The weak force lets the sun shine. For a century, every push and pull in the universe has fit into those four. Finding a fifth force would be one of the biggest discoveries in the history of science. The hint came from a group in Hungary studying how tiny atomic nuclei shed extra energy. They took a light element, added a jolt of energy, and watched the nucleus settle down. As it calmed, it released energy that turned into a pair of particles, an electron and its antimatter twin flying off together. Normally, the angle between that flying pair follows a smooth, predictable pattern. The more energy, the wider they spread, in a gentle curve physicists know by heart. But the Hungarian team saw a bump in the pattern. At one particular angle, far more pairs flew apart than the smooth curve allowed. A little spike sitting where nothing should be. And a spike like that has a natural explanation. It could mean the energy briefly made a brand new particle, one that instantly split into the electron and its twin. The angle of the spike even lets you estimate the new particle's weight, and it landed around 17 times heavier than an electron. If that particle is real, it would be a carrier of a force we have never met, a fifth force, whispering through the decay of tiny nuclei. The team saw the same strange bump in more than one experiment, using different elements, and each time the spike pointed to a particle of about the same weight. That repetition is what makes the claim so hard to wave away. Here is the honest truth, and it matters. No other laboratory has confirmed this. The signal has come so far mostly from one group and their equipment. In physics, an extraordinary claim only becomes real when other scientists, using other machines, see the very same thing. Until then, a bump in the data could be a genuine new force, or it could be a subtle flaw in one experiment, a quirk of the detector dressed up as a discovery. We have seen that trap before, with the heavy W boson. So right now, this possible fifth force sits in a strange limbo. It is exciting enough that labs around the world are building experiments to test it, hunting for the same spike in their own data. And it is unproven enough that no textbook has changed a single word. It might be the crack that adds a whole new force to nature. It might be nothing at all. Picture a lone hiker who swears she saw a creature unknown to science slip through the trees. She describes it in careful detail, and even sees it more than once. But until another person, with another camera, catches the same creature, the world can only wait, caught between wonder and doubt. The fifth force is that creature in the trees, glimpsed, described, and still waiting for a second witness. And while the world waits, another crack has been quietly widening, this one hiding inside the way certain heavy particles fall apart. Because some particles seem to be making a choice they were never supposed to make. Deep inside the world's biggest atom smasher, a heavy particle keeps falling apart in a way that looks like favoritism. The rulebook makes a promise about the electron and its two heavier cousins, the muon and the tau. It says every force treats all three exactly the same, caring only about their different weights. This is one of the most trusted ideas in all of physics, a rule so basic it feels almost sacred. To test that promise, scientists watch a heavy, short-lived particle called the beauty quark. When it falls apart, it can spit out either a pair of electrons or a pair of muons, and the rule says both should happen equally often. For years, one experiment at the Large Hadron Collider counted these decays, and it kept finding fewer muon pairs than electron pairs. The family looked lopsided. The muons seemed to be getting shortchanged. Excitement exploded across physics. Maybe a brand new force was reaching out and touching muons differently. Then, in 2022, the same team gathered far more data and looked again. The lopsidedness faded. With better counting, the electrons and muons came out even after all, exactly as the rulebook promised. One of the most exciting cracks of the decade quietly sealed itself shut. The story keeps going, because the family has a third cousin, the tau. The tau is a monster, about 3,500 times heavier than the electron. And when scientists study a different decay of the beauty quark, one that makes taus, they keep finding more taus than the rules allow. That gap has refused to fade. Different experiments, different years, the same stubborn excess of taus. On top of that, a handful of rare beauty quark decays show odd angular patterns, meaning the directions the leftover particles fly out, sitting a little off from what the math predicts. Small, nagging, and so far unexplained. So the flavour story is a mixed bag. One crack closed, another still glows. Honest scientists will tell you the Mon versus electron dream cooled off, while the tau puzzle keeps them awake at night. Picture 3 siblings and a parent who swears all 3 are treated exactly alike. You watch closely for years. The 2 younger children really do get identical treatment down to the last detail, but the oldest, biggest sibling seems to get something extra, again and again. Either you are miscounting somehow, or that parent has a secret rule they will not admit to. If the tau excess is real, it points to a new force that plays favourites, one that leans toward the heaviest members of the family and ignores the light ones. That would be a genuine crack, a force hiding just outside the rulebook, revealing itself only when the heaviest cousin is involved. Scientists are building sharper experiments right now to find out whether the tau gap is real or a mirage. And this whole puzzle drags an older, deeper question back into the light, one physicists have dodged for decades. The electron, the muon, and the tau are 3 copies of the same particle, identical except for their weights. The lightest one builds every atom in your body. The other 2 seem to do nothing at all, so why do they exist? Why did nature build the very same particle 3 separate times, then hide 2 of the copies away? Everything in your body is built from a tiny handful of particles, and nature made 2 spare copies of each for no reason anyone can find. Look closely at the matter you're made of. Ordinary stuff needs only a few basic pieces. There is the up quark and the down quark, which build every proton and neutron, and the electron that circles them. 3 little pieces make every atom in you, in this room and in the stars overhead. Nature did not stop at 1 set. It made 3. There is a second family, a set of heavier copies of the first. The electron has its heavier twin, the muon. The 2 quarks have heavier versions too. Then comes a third family, heavier still, topped by the tau and by a giant called the top quark, the heaviest particle we have ever found. 3 complete generations of matter, each a chunkier echo of the one before, and every heavier set falls apart almost instantly into the lighter ones. Here is the strange part. The heavier families do nothing for you. You are built entirely from the lightest set. The other 2 seem to serve no purpose at all. They flash into being inside cosmic collisions and giant machines, then vanish in a heartbeat. When scientists first stumbled onto the muon back in the 1930s, a famous physicist named Isidore Rabi summed up everyone's confusion in 4 words. Who ordered that? Nobody had asked for a heavier electron. Nobody could say why it was there, and all these decades later, we still cannot. The rulebook simply lists 3 families and moves on. It offers no reason for the number 3. Not 2, not 4, not 17. 3. That number is stitched into nature by hand, and no one knows who did the stitching or what it means. Picture opening a toolbox to build a house and finding every tool in 3 sizes. A normal hammer, a heavier hammer, and a giant hammer. Yet you only ever need the smallest one. The big ones sit there, perfectly made and completely useless. You would wonder who packed this box and what they knew that you do not. This missing reason matters more than it first seems. The pattern of the three families, their masses, and the way they shapeshift into one another might hide the answer to where mass itself comes from. Some physicists believe that if we ever crack the code of the three generations, we will finally understand why the neutrino weighs almost nothing, and maybe even why the universe is full of matter. The families could be a locked message from the deepest layer of reality, written in a language we have not learned to read. For now, it stays a real and stubborn mystery. The most powerful machines ever built have created all three families, studied them, and still cannot explain why there are three. It is a question hiding in plain sight, inside the very stuff you are made of. And the more physicists stare at the pattern of matter, the more they realize how little of it they can even see. Because when they weigh the entire universe, most of the matter holding the galaxies together gives off no light whatsoever. It is out there, it has gravity, and it is completely invisible. A galaxy is spinning so fast that by every rule we know, it should be tearing itself apart. Picture a galaxy, a vast pinwheel of hundreds of billions of stars turning slowly in the dark. Gravity is what holds it together, and the strength of that gravity depends on how much matter is packed inside. So think about our own solar system for a moment. The planets close to the Sun race around quickly, while the far-out planets crawl. Mercury zips along, while distant Neptune plods. That is how gravity behaves when most of the mass is bunched in the middle. Stars at the edge of a galaxy should act the same way, drifting slowly because they sit far from the crowded centre, where most of the visible matter lives. That was the firm expectation. They do not. In the 1970s, an astronomer named Vera Rubin measured how fast stars move at the outer edges of galaxies, expecting them to slow down. Instead, she found the outer stars racing around just as fast as the inner ones. It was as if Neptune circled the Sun as quickly as Mercury. The galaxies were spinning far too fast at their edges to be held together by the matter we can actually see. By all rights, those outer stars should have flung themselves off into empty space long ago. Something invisible was holding them in, some huge, unseen mass wrapped around each galaxy like a hidden cocoon, adding the extra gravity needed to keep the fast-spinning stars from escaping. Rubin had found the fingerprints of matter that no telescope could see. We call it dark matter now, and the more scientists looked, the more of it they found. It gives off no light, blocks no light, and seems to ignore ordinary matter completely except through the steady pull of gravity. And there is a stunning amount of it. For every pound of ordinary matter in the universe, every star, every planet, every person, there are roughly 5 pounds of this invisible stuff. That means the glowing universe you see, all the stars and galaxies blazing away, is a thin sprinkle floating on top of a vast invisible bulk. The cosmos is mostly built from something we have never held, never seen, and cannot yet name. Think of wind. You cannot see the air moving, yet you know it is there, because the leaves stream sideways and the flag snaps tight. Dark matter is like that. We cannot see it, but we watch whole galaxies bend and swirl around its pull. The evidence is written in the motion of the stars themselves. This much is rock solid. Galaxies really do spin too fast, and the gravity of the visible matter cannot hold them together. The pull of dark matter shows up in galaxy after galaxy, in the way clusters of galaxies move, and in the overall shape of the entire universe. On the fact that the pull is real, scientists agree completely. What the stuff actually is, though, remains a total mystery, and so physicists set out to catch a piece of it. They built detectors of almost unbelievable sensitivity and buried them deep underground, certain that sooner or later a single dark matter particle would stumble into their traps. They have been waiting for decades, and so far every trap has stayed silent and empty. In a laboratory almost a mile beneath a mountain, a tank of liquid waits in perfect darkness for a knock that has never come. If dark matter is a particle, then trillions of these particles should be streaming through the Earth and through your body every single second, much like the ghostly neutrinos. Almost all of them slip through solid rock as if it were open air, but once in a great while one might bump into an ordinary atom and give it the faintest possible nudge. Catch that nudge, and you have caught dark matter in the act. The trouble is that the nudge would be almost impossibly tiny, and the world is drowning in noise that could fake it. Cosmic rays raining down from space, natural radioactivity humming in the rocks, even a stray speck of dust could swamp the real signal. So scientists go to wild extremes. They build their detectors deep underground, under a mile of solid rock that blocks nearly everything falling from the sky. They fill them with ultra-pure liquid, often a heavy element called xenon, chilled and held perfectly still. Then they wait, watching for a single flash of light from a single atom getting knocked aside. These detectors are marvels of human patience. The biggest ones hold tons of liquid and can sense the tiny recoil of one atom among all those trillions. Each new generation is far more sensitive than the last, able to catch signals hundreds of times fainter than before. If a dark matter particle of the kind everyone expected were passing through, these machines should have seen it many times over by now. They have seen nothing. Search after search, year after year, the traps come up empty. For decades, the favourite candidate was a heavy, shy particle that barely interacts with anything. Experiment after experiment hunted for it, squeezing the space where it could possibly hide smaller and smaller. The particle kept failing to show up. It still clings to life as a bare possibility, but the easy, obvious version of the story has quietly slipped through everyone's fingers. So physicists face a deeply uncomfortable gap. The gravity of dark matter is certain. Whole galaxies bow to its pull, yet the stuff itself has never once been caught in a laboratory. We can feel its grip stretched across the entire cosmos, and we cannot find a single grain of it on Earth. Imagine you know a huge animal lives in a forest. You see its footprints everywhere, whole trees shoved aside, rivers dammed up. You set the finest traps money can buy, all through the woods, and you wait 30 years, and you never catch it. You never glimpse it, never hear it, never find a single hair. You would start to wonder whether the creature is far stranger than you thought, or whether you have badly misunderstood what left those tracks. That exact doubt has begun to crack the field wide open. If the particle stubbornly refuses to appear, some scientists have started to wonder if they have been hunting the wrong thing all along, and that led a bold handful of them to ask a truly dangerous question, one that most physicists found almost unthinkable. What if there is no invisible particle out there at all? What if the thing we got wrong is the law of gravity itself? One physicist looked at the spinning galaxies and made a radical claim. Maybe nothing invisible is out there, and our law of gravity is simply wrong. For centuries, the laws of gravity have passed every test we could throw at them. Drop an apple, launch a rocket, steer a probe to the edge of the solar system, and gravity behaves exactly as predicted. So when galaxies spin too fast, the natural move is to add invisible matter and keep the trusted law of gravity untouched. In 1983, a physicist named Mordechai Milgram tried the opposite approach. He suggested that gravity itself changes when its pull grows extremely weak, far fainter than anything we ever feel here on Earth, out in the lonely edges of galaxies. Adjust the law of gravity in that whisper-faint regime, he showed, and the fast-spinning stars suddenly make perfect sense, with no dark matter needed at all. The extra pull comes from a new rule of gravity, hiding where gravity is weakest. This idea, called modified gravity, has one shocking strength. When you point it at a single galaxy, it works astonishingly well. Give it only the visible matter, and it predicts how that galaxy spins with eerie accuracy, sometimes fitting even better than dark matter does. Over and over, from tiny dwarf galaxies to giant spirals, this one simple rule nails the motion of the stars. For a theory that many scientists dismiss, it wins a surprising number of contests, but modified gravity carries a serious weakness, and it appears the moment you zoom out. On the scale of giant galaxy clusters, the idea starts to struggle. It has real trouble explaining the oldest light in the universe, the faint afterglow left over from the Big Bang, which dark matter fits beautifully, and it wrestles clumsily with how the very first galaxies formed. For those enormous cosmic questions, invisible matter still does a far better job. So physics is left with two rival stories. One says the universe is packed with unseen particles we simply have not caught yet. The other says there are no such particles, and our law of gravity needs rewriting. Most physicists lean toward dark matter because it explains the whole universe, from the smallest galaxy to the largest structures in the sky. but a stubborn minority points to those beautiful galaxy predictions and insists modified gravity is telling us something real that we should not ignore. Imagine every map you own shows a mountain in the wrong place. You could decide there is a hidden, invisible mountain that no one can see. Or you could decide your maps were drawn with a flawed rule, and the mountain was never there to begin with. Both ideas could explain what you observe. Figuring out which one is true is the entire game. For years, the debate sat in a stalemate, each side scoring its points and refusing to yield. Dark matter explained the big cosmic picture. Modified gravity explained the individual galaxies. Neither side could land a knockout blow. Then the sky itself delivered a test that seemed to settle everything. A colossal collision unfolding across millions of years. Two vast clusters of galaxies had slammed head-on into each other, and in the wreckage they left behind, scientists found something that dark matter explained with ease, and that modified gravity could barely explain at all. Far across the universe, two enormous clusters of galaxies collided head-on, and the wreckage left behind a smoking gun. A galaxy cluster is one of the largest things that exists. Hundreds or thousands of galaxies bound together, floating inside a vast cloud of hot gas. That gas holds most of the ordinary, visible matter, far more than all the stars combined. Now imagine two of these giants crashing into each other at millions of miles per hour. That truly happened, long ago, in a place scientists call the bullet cluster. When the two clusters smashed together, something revealing took place. The galaxies themselves, spread far apart with mostly empty space between them, sailed right past one another like two swarms of bees passing through each other with no collisions. But the enormous clouds of gas filling the space between the galaxies slammed together and piled up. That gas got stuck in the middle, slowed by the impact, glowing white-hot from the crash. Most of the visible matter ended up trapped right there in the centre. Here is the key move. Scientists can also map where the gravity is, including the gravity of matter they cannot see. They do it by watching how the cluster's mass bends the light of even more distant galaxies behind it, warping and smearing their images like a giant lens made of gravity. So the scientists measured two separate things, where the visible matter sat and where the gravity was actually centred. The two did not match. The visible matter, the hot glowing gas, was stuck in the middle from the crash, but the gravity was centred on two separate clumps sitting far off to either side, exactly where invisible matter would be if it had sailed straight through the collision untouched, just like the galaxies did. The mass and the visible stuff had come apart. You could see the ordinary matter in one place and feel the gravity tugging from somewhere else entirely. For dark matter, this is a clean and stunning victory. Invisible particles would not crash and pile up the way gas does. They would glide right through each other and keep going, carrying their gravity out to the sides. That is exactly what the map reveals. Many scientists call the bullet cluster the closest thing we have to seeing dark matter with our own eyes. For modified gravity, the same picture is a nightmare. If there were no invisible matter, the gravity should stay glued to the visible gas right in the middle. Instead, it marched off to the sides, faithfully following something unseen. Supporters of modified gravity have worked hard to explain the collision, and they still argue their case. But for most physicists, this cosmic crash tipped the scales hard toward dark matter. Picture two trucks colliding and spilling their heavy cargo across the road, while the drivers, somehow invisible, walk away unharmed and stand off to the side. If you could only feel where the drivers were and never see them, you would notice that the true weight of the crash had quietly moved away from the wreckage. That is what the gravity did here. It walked away from the visible mess and stood off in the dark, so dark matter's grip on physics tightened. The invisible stuff is real. It is everywhere, and it helped shape the whole cosmos. Yet as strange as invisible matter is, it makes up only about a quarter of the universe. Something far stranger fills the rest, a force pushing all of space apart, and it makes dark matter look almost ordinary. The entire universe is flying apart, and instead of slowing down, it is speeding up. For most of the last century, scientists knew the universe was expanding. Every galaxy is rushing away from every other one, carried along by the leftover motion of the Big Bang. The big question was how quickly that expansion was slowing down. Gravity pulls everything together, so surely the great outward rush should be losing steam, like a ball thrown into the air that slows as it climbs. The only real question seemed to be whether the universe would coast outward forever or someday fall back together. In 1998, two rival teams set out to measure that slowing. They studied a special kind of exploding star, a supernova so predictable in its brightness that scientists can tell exactly how far away it is from how faint it looks. By measuring these explosions across billions of light years, the teams could clock how the expansion had changed over the long history of the cosmos. The answer stunned everyone, and both teams were slapped with the same shock. The expansion was speeding up. Galaxies are flying apart faster and faster as time goes on. Something is pushing the universe outward, overpowering the combined gravity of every scrap of matter in existence, and its grip keeps growing stronger. Scientists named this mysterious push dark energy. It appears to be a strange kind of energy woven into empty space itself. The more space there is, the more of this energy appears, and the harder the outward push, which is why the expansion keeps accelerating. This discovery was so important and so solid that it earned the Nobel Prize. The acceleration is confirmed beyond serious doubt. But what dark energy actually is, nobody has any idea. The name is just a label slapped onto a total mystery. And it is the main event of the whole universe. Add everything up, and the picture is humbling. Everything you have ever seen or touched, every star and planet and living thing, all the ordinary matter combined, makes up only about 5 parts in 100 of the universe. Dark matter, the invisible stuff, is around a quarter, and all the rest, roughly 7/10 of everything that exists, is dark energy. The cosmos is ruled by two things we cannot see and do not understand. Picture a loaf of raisin bread rising in the oven. As the dough swells, every raisin drifts away from every other raisin. Now imagine the dough rising faster and faster, ripping the raisins apart at ever greater speed. The raisins are the galaxies. The rising dough is space itself. And whatever is forcing that dough to rise faster and faster is dark energy, the greatest unknown in all the sky. So the universe you thought you knew is mostly darkness. A thin foam of glowing matter floats in a vast sea of invisible mass, and all of it is being carried apart by an unseen force that has no name and no explanation. And now, brand new maps of the sky have begun to whisper something that could shatter the simplest picture of dark energy. The force everyone assumed was steady and eternal might be changing. Reading the light of millions of galaxies, scientists have caught a faint hint that dark energy could even be growing weaker over time. It might, slowly, be fading. For years, physicists assumed dark energy was perfectly steady, and now the largest map of the universe ever made is hinting that it might be slipping. The simplest idea about dark energy is that it is a constant, a fixed amount of push baked into every scrap of empty space, exactly the same yesterday, today, and 1 billion years from now. Einstein himself once wrote a version of this into his equations, a steady, unchanging energy of the vacuum. For decades, this simple picture fit the data well enough, and most scientists assumed it was the final answer. To test it, scientists built a remarkable instrument that maps galaxies across the sky in staggering numbers. It stares out at the heavens and measures the exact distances to millions upon millions of galaxies, building the biggest 3-dimensional map of the universe ever created. And because light takes billions of years to reach us, looking far across space is also looking far back in time. So this map lets scientists watch how dark energy behaved in the distant past and compare it to how it behaves now. If dark energy is truly constant, its strength should look identical at every era of cosmic history. But when the first big batches of this data arrived, around 2024 and 2025, they hinted at something strange. Dark energy may have been a little stronger long ago and grown weaker over time. The great push might be fading. If that result holds up, it would overturn the simplest picture completely. Dark energy would be something dynamic, something that changes and evolves, and that would demand a whole new understanding of what it even is. It could even rewrite the future of the universe, changing whether space expands forever or eventually does something we have never imagined. Here is the crucial caution. This is only an early hint. The signal is modest. the kind of tension that has appeared before in physics and later melted away once more data came in. Some scientists are thrilled, convinced this is the first solid sign that dark energy is alive and changing. Others urge patience, suspecting a subtle error in the measurements that will vanish as the map keeps growing. Both camps agree on one thing: the stakes could hardly be higher. Imagine a lamp that everyone believed shone at a fixed brightness forever. Then you dig up old photographs suggesting it once burned brighter and has slowly dimmed over the years. If those photos are right, everything you assumed about the lamp is wrong. But old photographs can fade and mislead, so you check again, carefully, before you trust your own eyes. Right now, the world's cosmologists are doing exactly that, gathering more data to learn whether dark energy is steady or slipping. Bigger, sharper maps of the universe are already on the way. Within a few short years, we may finally know whether the dominant force in the cosmos is eternal and unchanging, or slowly dying. Whichever way it falls, dark energy already hides a far deeper embarrassment, a prediction so wildly wrong that it may be the single worst guess in the history of science. When physicists try to calculate how much energy empty space should hold, the math hands them a number so absurd that, if it were true, the universe would have destroyed itself in its very first instant. Physics contains one prediction so wildly wrong that scientists openly call it the worst guess in the history of science. Remember the boiling vacuum, that sea of virtual particles flickering in and out of empty space. Those flickers carry energy, so empty space should not truly be empty of energy at all. It should hold a background hum, a built-in energy of the vacuum, and that vacuum energy is exactly the kind of thing that could act as dark energy, gently pushing the whole universe apart. So physicists tried to calculate it. Using the quantum rules that describe the flickering vacuum, they added up how much energy empty space ought to contain. The math handed back an answer, and that answer was catastrophic. The predicted energy of empty space came out staggeringly, monstrously huge, far, far larger than the tiny amount we actually see pushing the universe apart. The gap between the prediction and reality is almost impossible to put into words. The calculated value is bigger than the measured one by a factor written as a 1 followed by more than 100 zeros. There is no other wrong prediction anywhere in the entire history of science that even comes close to this staggering size. Think about what that really means. If empty space truly held as much energy as the simple calculation predicts, the outward push would be so violent that space would have ripped itself to shreds in the first instant of the universe. Atoms could never form, stars could never gather, galaxies could never be born, you could not exist. Everything would have been torn apart before the universe drew its first breath. Instead, the real energy of empty space is fantastically tiny, just barely enough to gently accelerate the expansion over billions upon billions of years. Somehow, the enormous vacuum energy that the math demands gets almost perfectly cancelled away, leaving behind only the faintest whisper. Almost, but not quite. 0. And no one knows what does the cancelling or why it stops at such a precise and tiny leftover. Imagine you calculate the weight of a single feather, and your math insists it should weigh more than every mountain, ocean and planet in existence combined many times over. You would know at once that something was badly broken in how you were doing the sum, yet the feather sits there in your palm weighing almost nothing at all. That is the situation physicists face with the energy of empty space. Our best theory overshoots plain reality by an amount too vast for the mind to hold. This is one of the deepest cracks in all of physics, and here is what makes it so unsettling. It will not go away with better measurements. The vacuum energy really is tiny, measured carefully and confirmed, and our best math really does predict something enormous. Both facts are solid. Bridging the gulf between them may require ideas that no one has even dreamed up yet. The trouble runs deeper still, because scientists cannot even agree on how fast the universe is expanding right now, today. Two of the best methods ever devised for measuring that speed give two clearly different answers, and the harder scientists look, the sharper their tools become, the more firmly those two numbers refuse to meet. Two teams set out to measure how fast the universe is expanding, and they came back with answers that stubbornly refused to agree. The universe is stretching, carrying every galaxy apart from every other. The speed of that stretching is one of the most important numbers in all of science, because it tells us the size of the cosmos, its age, and its ultimate fate. So scientists have measured that speed with enormous care, using two completely different methods, and that is exactly where the trouble begins. The first method looks deep into the young universe. Scientists study the oldest light in existence, a faint glow left over from just after the Big Bang, still filling the entire sky today. Hidden inside the tiny ripples of that ancient light is a precise record of how fast the early universe was set to expand. From those ripples, scientists calculate today's expansion speed with great confidence. The second method looks at the nearby universe, here and now. Scientists build a ladder of distances, starting with special stars that pulse at a steady, reliable beat, then reaching out to those dependable exploding stars, measuring how fast galaxies rush away at carefully known distances. This gives a direct reading of the expansion speed in our own cosmic neighbourhood. Both methods are brilliant. Both have been sharpened and rechecked for years, and they flatly disagree. The nearby measurement comes out faster than the early universe prediction, by close to 1 part in 10. That might sound small, but for measurements this precise, it is a chasm. And here is the truly unsettling part. As both methods have grown sharper and more careful, the gap between them has held firm and grown more certain. Physicists have a name for this standoff. They simply call it the tension. So either one of these superb methods hides a mistake that nobody has managed to find, or, far more thrilling, something is genuinely wrong with our understanding of the universe between the ancient past and now. Perhaps a strange form of energy in the early cosmos, or some unknown ingredient we have never accounted for, is quietly bending the two numbers apart. Nobody yet knows which answer is right. Imagine measuring your own height in two different ways. One tape measure, used with great care, says you are a certain height. A second method, also careful, insists you are noticeably taller. You try again and again, sharpening each method, certain the two will finally line up. Instead they dig in, each one growing more confident, refusing to meet in the middle. At that point you would know something real was going on, hiding either in one of your methods or in your understanding of your own body. That is precisely where cosmology sits today. The universe seems to be expanding at two different speeds, depending on how you choose to measure it, and no one can explain the mismatch. It might turn out to be a hidden error waiting to be found, or it might be the crack that finally splits our whole model of the universe wide open. These giant puzzles stretch across the entire cosmos, but the same maddening pattern shows up on the tinier scales too, inside a particle sitting right at the heart of every single atom. Even the humble proton has kept a secret that split scientists apart for years. For a while, one of the most basic measurements in all of physics, the size of a single proton, gave two different answers depending on how you looked at it. A proton is the tiny positive particle sitting at the centre of every atom. It is one of the most common objects in the universe, and physicists were sure they knew its size very well. To measure it, they used hydrogen, the simplest atom of all, just a single electron circling a single proton. By studying the light that hydrogen gives off, with fantastic precision, scientists could read off the proton's radius. For years, that number was settled, trusted, and printed in every textbook. Then someone tried a clever new version of the experiment. Instead of an ordinary electron, they built a strange atom using a muon, the electron's heavy cousin. Because the muon is about 200 times heavier, it orbits about 200 times closer to the proton, hugging it far more tightly. And the closer a particle orbits, the more sharply it feels the proton's exact size. So this muon-based atom promised the sharpest measurement of a proton ever made. It was like trading a blurry lens for a powerful magnifying glass pressed right against the surface. In 2010, that sharper measurement came back, and it delivered a jolt. The muon reported that the proton was smaller than the electron had ever measured. The two numbers disagreed by a small but unmistakable amount, far larger than the tiny margin of error allowed. Two ways of measuring the same simple particle had produced two different sizes. Scientists were baffled. Some began to wonder whether the muon was feeling a brand new force that the electron could not, a fresh crack in the rulebook hiding inside the humble proton. For several years, the proton radius puzzle was a genuine mystery, argued over in laboratories all around the world. Then, slowly, the fog began to lift. Scientists went back and redid the ordinary hydrogen measurements with even greater care, hunting for hidden mistakes. Fresh experiments rolled in, and most of them drifted toward the smaller size, the very one the muon had seen. The gap started to close. Today, most physicists believe the puzzle came from subtle errors in the older, harder measurements, rather than from any exotic new force. The proton is most likely just a touch smaller than we first thought. It stands as a rare and hopeful story, a crack that appeared, terrified everyone for years, and then mostly healed once the measurements finally got good enough. Imagine two people measuring the same marble. One uses an old worn ruler and gets a certain number. The other uses a brand new precision tool and gets a slightly smaller number. For a while you have no idea who to trust. Then you inspect the old ruler and discover it had stretched, just a hair, over the years. The mystery dissolves, and you finally learn the marble's true size. That is how most physicists now see the proton puzzle, a scare that turned out to be a measuring problem, not a revolution. But not every measurement mystery has resolved so kindly. One of them, about a particle even simpler than the proton, has resisted every attempt to crack it for decades. Two careful ways of timing how long a neutron lives keep handing back two different answers, and so far nobody on Earth can make them agree. A lone neutron, floating free outside an atom, does something strange. It dies, and no one can agree on exactly how long it takes. Inside the nucleus of an atom, neutrons can live essentially forever, but pull a neutron out on its own, set it loose, and it becomes unstable. After a while, it falls apart, breaking down into a proton and a couple of other particles. On average, a free neutron survives about 15 minutes before it decays. On that much, everyone agrees. The mystery lives in the exact number of seconds, and there are two very different ways to measure it. The first way is called the bottle method. Scientists trap a batch of free neutrons inside a special container, a kind of bottle they cannot easily escape. Then they wait, and after some time they count how many neutrons are left. Fewer neutrons remaining means more have decayed away. By tracking how fast that count drops, they measure the neutron's lifetime directly. The second way is called the beam method. Instead of trapping neutrons, scientists send a steady beam of them flowing through a chamber. As the neutrons decay in flight, they leave behind protons, and scientists carefully count those fresh protons appearing. More protons means more decays have happened. From that count, they calculate the lifetime a completely different way. Both methods are careful, both have been refined for decades, and they disagree. The beam method says the neutron lives about 9 seconds longer than the bottle method claims. 9 seconds out of a 50-minute lifetime sounds small, but the measurements are so precise that the gap should not exist at all. It has stubbornly refused to close year after year, no matter how carefully scientists check every part of their work. Something is wrong, and there are two kinds of answers. The dull possibility is that one method hides a flaw, some tiny leak in the bottle or a miscount in the beam that nobody has spotted yet. The thrilling possibility is far stranger. What if, once in a while, a neutron does not decay in the normal way at all? What if it sometimes vanishes into something invisible, an unknown particle, maybe even a piece of dark matter? If a small fraction of neutrons quietly slipped away into the dark, the two methods would naturally count differently, and the mystery would become a doorway to new physics. Imagine timing how long a block of ice takes to melt, using two methods at once. One method counts how much ice is left sitting in the bucket. The other counts the drips of water flowing out the bottom. If those two clocks disagree, then either one of them is broken, or some of the ice is escaping in a way you never expected, turning into something other than water. That second possibility is exactly what keeps these physicists awake at night. Right now, this puzzle is still wide open. Scientists are building sharper experiments to hunt down that 9-second gap, because the answer could be a boring mistake, or it could be a crack connecting the humble neutron to the invisible universe. All these cracks, from the tiniest particle to the widest reaches of space, share one hidden root. Our two greatest theories of reality, the ones that explain almost everything, flatly refuse to work together. Where they meet, physics itself falls apart. Physics stands on two towering theories, and when you force them to work together, they explode. Everything we have explored flows from one of two grand ideas. The first is the Standard Model, the quantum rulebook that governs the tiniest particles with breathtaking accuracy. The second is Einstein's theory of gravity, which describes space, time, and the sweep of stars and galaxies with equal perfection. On their own, each one is a masterpiece. Between them, they explain nearly every experiment ever performed. There is only one problem. They cannot both be fully true in the same place at the same time. Each theory reigns beautifully in its own kingdom. The quantum rulebook rules the very small, the world of atoms, particles, and forces. Einstein's gravity rules the very large, the world of planets, stars, and the shape of the cosmos. For almost everything, these two kingdoms stay politely apart, and each theory handles its own territory without stepping on the other. But there are places where the very small and the very heavy collide, and there, both theories must speak at the very same moment. When physicists try to make them speak together, to describe gravity using the quantum rules, the math shatters. Instead of clean answers, the equations spit out nonsense, infinities, numbers that blow up to meaningless, impossible sizes. The two greatest ideas in all of physics, each one flawless when left alone, dissolve into gibberish the instant you combine them. Something at the very foundation of reality is deeply and truly broken. This is no small technical snag. It means we do not actually understand reality at its deepest level. We hold two separate rulebooks and possess no master rulebook that contains them both. And there are real places in the universe where this failure bites hard. At the centre of a black hole, where enormous mass is crushed into a single tiny point, both gravity and the quantum world scream for attention at once, and our physics simply stops working. The same total breakdown happens at the very first instant of the Big Bang, the birth of everything that is. At the exact moments that matter most, our finest theories go blind. Physicists have spent decades trying to build that missing master theory, a single set of rules that would finally join the quantum world and gravity into one seamless whole. Some call their leading attempt string theory. Others chase entirely different paths. So far, not one of these grand ideas has been confirmed by a single experiment. The deepest crack in all of physics remains wide open. Imagine you have two perfect maps of the same city. One is written entirely in one language, the other in a completely different language, with no shared words and no way to line up the streets. Each map is flawless on its own, but lay one on top of the other and nothing matches. You cannot travel using both at once. Until someone finally draws a map that speaks both languages, whole regions of the city stay forever out of reach. That unreachable region is exactly where the biggest answers hide. The birth of the universe, the heart of a black hole, the true nature of space and time themselves. And lurking inside these unfinished theories is an unsettling possibility. The empty space that fills the universe might not be as stable as it looks. It may be sitting quietly in a trap. And one distant day, in principle, it could fall. There is a strange idea buried inside modern physics. The emptiness of space might be resting in a trap waiting to collapse. We have seen that empty space is full of energy, humming with the restless quantum vacuum. Physicists usually assume that space has settled into its lowest, calmest, most stable state, like a ball that has rolled all the way to the bottom of a valley and come to rest. Once it sits at the very bottom, nothing can make it fall any further. It is safe forever. But when scientists measure two key numbers, the mass of the Higgs particle and the mass of the heaviest quark, the top quark, and feed them into their equations, they get an uneasy result. The vacuum of space might not be sitting at the true bottom after all. It may be resting in a shallow dip partway down the slope, with an even lower, deeper valley waiting somewhere below it. Physicists call this a false vacuum. Picture a ball that has stopped in a small hollow on the side of a long hill. It looks perfectly settled. It could sit there for ages. But it sits above the true bottom, and if something ever nudged it out of that little hollow, it would roll all the way down to the real valley far below. If the vacuum of our universe is caught in one of these traps, then in principle it could someday escape. Quantum physics allows a strange trick called tunneling, where something can suddenly slip through a barrier it normally could never cross. A tiny bubble of the true lower vacuum could pop into existence somewhere in space, and once it appeared, it would grow, racing outward at the speed of a light, rewriting the laws of physics inside it as it swept across the cosmos. Now here is the part that matters most, so that no one loses a moment of sleep. This is a theoretical possibility drawn from current measurements, and it is soaked in uncertainty. Even if the vacuum really is in such a trap, the calculations say the wait before anything could happen is almost unimaginably long, far longer than the current age of the universe multiplied by a number with a dizzying pile of zeros. The universe has already lasted billions of years, and it would almost certainly last countless billions more, utterly peaceful, before any such event became likely. This is a puzzle about the deep nature of space, and a comfortably distant one. What makes it fascinating is what it might be hinting. If the vacuum truly sits in a false, delicate state, that could be another clue that the standard model is incomplete, that new particles or forces we have not yet found are quietly helping to hold empty space steady. The stability of nothing itself could be pointing us toward deeper laws. Picture a marble resting in a little dent near the top of a long slope. It looks perfectly still and safe, yet a much deeper drop waits just past the edge of the dent. The marble may sit there far longer than you will ever live, yet it still has further to fall, and that single fact tells you the hillside is more complicated than it first appeared. If even the emptiness of space might hide a secret like this, then perhaps the deepest rules of all are less fixed than we believe. Some scientists have dared to ask whether the constants of nature, the fixed numbers baked into physics, are truly the same everywhere in the universe. Scientists have always assumed the basic numbers of physics are the same everywhere, and a handful of daring measurements have dared to question that. Nature runs on a set of fixed numbers, called the constants. They set the strength of each force and the properties of each particle. One of the most important is a number that fixes the strength of electricity and magnetism, the very same number we met while testing the electron. For as long as there has been physics, everyone has assumed these constants are truly constant, identical in every galaxy, every direction, and every moment since the beginning of time. It is one of the bedrock assumptions of all science. Then some astronomers went looking, and what they thought they found was startling. To test whether the constants really hold everywhere, scientists used the light from quasars, blindingly bright beacons in distant galaxies, some so far away that their light has travelled for billions of years to reach us. On its long journey, that light passes through drifting clouds of gas, and the gas drinks in certain exact colours, leaving a pattern of dark lines in the light, like a barcode. The precise spacing of those lines depends on that key constant, the strength of electromagnetism. So by reading the barcodes printed on ancient faraway gas, scientists can check whether the constant held the same value long ago and far across the universe. A few teams reported something strange. The barcodes seemed to be very slightly shifted, hinting that the constant might have carried a tiny bit different value in the distant past, or even that it changes depending on which direction you look in the sky. If that were real, it would be earth-shaking. A constant of nature that quietly changes would mean the laws of physics themselves are not truly fixed, and might drift across space and time. Suddenly everything would be back on the table. But this claim rests on shaky ground, and most physicists are deeply skeptical. The shifts being measured are fantastically tiny, sitting right at the ragged edge of what the instruments can even detect. Other teams, using different telescopes and different methods, have hunted for the same effect and found nothing at all, no variation whatsoever. The most likely explanation is that the original hints came from subtle flaws in the instruments, tiny distortions masquerading as a changing constant. The evidence stays contested, and the mainstream view holds that the constants are almost certainly exactly that, constant. Imagine opening nature's rulebook and finding that a few of the numbers in one far corner of the page look faintly smudged, as if they might read a little differently than all the rest. It could be a real difference, a stunning clue that the rules shift from place to place, or it could simply be a smudge on your glasses. Until you clean the lens and check again with sharper eyes, you cannot be sure what you're truly seeing. That is where this mystery rests today, unconfirmed and hotly debated, a possible crack that may well turn out to be nothing at all. We have journeyed a very long way, from a single wobbling particle to the farthest edges of the observable universe, gathering cracks at every step. Now it is time to step back, take in the whole strange map at once and ask what all of these cracks standing together might be trying to tell us. We began with one tiny particle wobbling the wrong way, and we have ended up questioning the stability of space, the fate of the universe, and the deepest rules of reality. Look back over the whole trail we followed. A muon spinning a hair too fast. An electron's perfect wobble resting on a number 2 great labs cannot agree on. A boson that seemed far too heavy until it wasn't. Ghostly neutrinos that broke the rulebook simply by having any weight at all. A universe made of matter that, by the rules, should have wiped itself out into nothing. Invisible mass gripping every galaxy in the sky. A nameless force shoving all of space apart, maybe fading even as we watch. And 2 magnificent theories that flatly refuse to speak to each other. Some of those cracks have already healed. The too heavy boson turned out to be a likely measurement flaw. The proton's puzzling size mostly resolved once the tools grew sharp enough. That is science working exactly as it should, testing itself, correcting itself, throwing out its own mistakes without mercy. But others stand rock solid and completely unexplained. Neutrinos truly carry mass, and the rulebook has no room for it. Matter truly won its ancient war with antimatter, and we still do not fully know how. Dark matter truly grips the galaxies, and we have never caught a single piece of it. The universe truly is accelerating apart, driven by something we cannot name. These are real gaps in our deepest understanding of everything, waiting to be filled. And that is the thrilling part. Every one of these cracks is a place where the known rules run out, and something new might be waiting on the far side. The Standard Model is the most tested, most successful theory humans have ever built. It has passed every single experiment thrown at it for half a century, and we know, with total certainty, that it is incomplete. The next great leap in physics is hiding inside exactly these cracks. Here is what that means for you. Everything you have ever seen, every star and atom and living thing, makes up only about 5 parts in 100 of the universe. The other 95 parts are a mystery that no one has solved. We're all living inside the single greatest unanswered question in the history of science, and the answers are still out there, waiting to be found. Think of each crack as a door standing slightly open, set into a wall that everyone believed was solid stone. Behind those doors could be new particles, new forces, extra dimensions, a whole hidden layer of reality we have only begun to glimpse. Every open door is an invitation to walk through. The generations before us built the rulebook and then found its edges. The discoveries that finally explain the darkness may come from people alive right now. They might even come from someone listening to these very words. The muon is still wobbling. The neutrinos are still pouring through your body by the trillions. The universe is still flying apart, and the doors are all still standing open, waiting for someone curious enough, patient enough, and stubborn enough to step through. The crack in physics is the way in, and the greatest discoveries of all are still ahead of us, hidden in the dark, waiting for the ones brave enough to go looking.